let's move on from here. Now that we've seen the Thevenin pattern, what I'd like to do is continue analyzing this a little bit more. As I said earlier, the Thevenin pattern replaces the arbitrary network N, and VTH here in the Thevenin network is simply the open circuit voltage seen at the terminal pair. In other words, if I looked at network N and I simply measured the voltage at the terminal pair, and it has to be a open circuit voltage that is without anything connected there, then whatever voltage I measure there would be the Thevenin voltage. Notice that you can see the same thing here. If I measured the voltage at that point without any external excitation with an open circuit here, then VTH would directly appear at the terminal, and I would be able to measure the Thevenin voltage. Similarly, what is RTH? RTH is simply the resistance of the network seen at the terminal pair with all the voltages VMs and all the currents INs set to 0. In other words, the way you can find the Thevenin resistance of a network is simply set all the voltages and all the currents to 0, and then go ahead and simply measure the resistance looking into that terminal pair, and that will give you RTH. Again, as a quick summary, given any network N, and in this case a network with independent voltage and current sources, I can find the Thevenin equivalent, which comprises a Thevenin voltage VTH and a resistance RTH as follows. I open circuit the connection. In other words, I don't connect anything to the terminal pair, but I'm measuring the voltage V. I measure the open circuit voltage there, and that is my VTH. Then I turn off all my current sources and voltage sources inside the network N and simply measure its resistance, and that is RTH. So that's how I can get RTH and VTH by measurement. And for the purpose of computing some property such as the voltage, when an external excitation is applied, I can use those values of VTH and RTH to replace the entire arbitrary network N with this Thevenin equivalent pattern. This is a very, very powerful technique, and we will see some examples of this shortly. Okay, so we are ready to define the Thevenin method. So in the Thevenin method, you are given some network N. It may be a horrendous network with a whole bunch of voltage sources and current sources and resistors and so on and so forth. And you have some other external network E, so E for external. Then what I can do is, by the Thevenin method, I can break this down into a simpler problem as follows. What I would do as a first step is I would replace the network N with this Thevenin equivalent. And then as my second step, I would solve with the external network E. So in other words, what I would do is that I would replace the network N with its Thevenin equivalent as my first step, and then I would go ahead and solve with the external network E in my second step. And notice that I can compute RTH and VTH for the Thevenin equivalent using the discussion from a few minutes ago, where I can measure it by measuring the open circuit voltage and the effective resistance of the network with all sources turned off. Or I can also compute it by using superposition and turning off each of the voltages one by one. I can do it in either way. So this is the Thevenin method. Okay, again, as a first step, I replace the network N with the Thevenin equivalent, and then I solve with the external network E. Now, you might wonder, when is this useful? So it turns out that in many cases where if all you're interested in is some value, a V for example, and you don't really care about what's going on inside this horrendous network N, then you can simplify your life tremendously by replacing that entire network with its Thevenin equivalent and then solving the circuit for the voltage V based on that Thevenin equivalent. Again, this is a process where you divide up the problem into two simpler components, finding a Thevenin and then solving the resulting circuit. Let us now move on to an example and go to our old faithful little circuit here. And in this example, let us say that my goal here is to find out the current I1. Okay, let's say all I care about is to find out the current I1. Now, of course, I can go ahead and apply the node method and do it. But let us say that in this case, I want to apply the Thevenin method and use this as an example. And I'm going to show you how simple it can get. So to apply the Thevenin method, remember the first part was to identify some sub-network and replace that by its Thevenin equivalent. So what I'm going to do is I'm going to identify this network here as the arbitrary network N, whose Thevenin equivalent I am going to find. And then I'm going to view the network on the left-hand side, the voltage and resistance, as the network E. And the reason I'm going to do that is, notice that if I replace network N with a Thevenin equivalent, which would be simply a resistance and a voltage, notice that the resulting circuit would be very simple to analyze because it would have a pair of voltages and a pair of resistances in series. Let me go ahead and find the Thevenin equivalent for network 1 in step 1 of the Thevenin method. Okay, so I'm going to replace network N by its Thevenin equivalent. So my network E is going to stay the same. So E hasn't changed. I'm trying to figure out the value of I1. And I want to replace the network N with its Thevenin equivalent. So let me go ahead. So the Thevenin equivalent will fit in here, okay, into this box. And let me draw the Thevenin pattern just to be clear, okay, where this is R Thevenin and this is V Thevenin. I'm going to replace network N with its Thevenin equivalent, and in order to do that, I need to find out the values of RTH and VTH, and let me go ahead and do that next. Continuing with step 1 of the Thevenin method, I have my network N, and I need to find out VTH and RTH for that network N. And again, as a reminder, this is what I have for VTH and RTH. Okay. So let me first find out VTH. And as I told you earlier, VTH is simply the open circuit voltage of the network N. So how do I find out what the open circuit voltage of that network N is? Well, it's pretty straightforward. Let me draw the network here. So I have an R2 here, and I have a current I here. And the open circuit voltage is my Thevenin voltage, VTH. So here's your simple pattern. I have a current I that is flowing into a resistance R2, and so therefore VTH is simply I times R2. Okay, so that gives me my VTH. So the second step, I need to find out RTH. And the way I'm going to find out RTH is I'm going to turn off all the independent sources inside network N and then measure the resistance looking in. So this was my network from before. This corresponds to this network. I'll do the same now. So I'm going to put my network in there. And the difference is that I'm going to turn off all the voltages and currents that are independent inside that network. So as I draw it out, R2 stays the same. But here, what I'm going to do is I'm going to turn off my current source and open circuit that. So I'm going to turn off my current source, and so now RTH will simply be the resistance looking in. That is easy enough to do. So RTH is simply R2. So there you have it. I've computed VTH and RTH, and that lets me develop my Thevenin network, and I'm ready for step 2. So as I said earlier, VTH and RTH are given by these two values, and what I'm going to do is I'm going to replace the network N with its Thevenin equivalent. Network E stays the same. I show that here. That hasn't changed. But now what I'm going to do is I'm going to replace the network N with its Thevenin equivalent, like so. Okay, where I get the RTH in series with the VTH, and where VTH is given by IR2 and RTH is given by R2. Okay, so at step 2, I now need to solve with the external network E applied to the Thevenin equivalent network that has replaced the original network N. So this is again a very simple circuit, and recall all that I cared about was I1, and so let me let you think for a couple of seconds about what the value of I1 is before I go and do it myself.